Hi, I'm Kaye from the School of Physics and Astronomy, and I'm going to give you a bit of a tour around the science precinct here. So we've got green chemical futures right behind me. We've got the library, which is focused for engineering and science. We've got the science faculty office. We've got the student learning lounge, which is just for science students to hang out, work on assignments together and spend time together. We've got the science student services just here, so if you've got any questions about your enrolment, which subjects you should be doing, then you can head in there. And then we've got the main physics building here. So this is nice because it's got all of the student laboratories in there, and also the offices of most of the physics staff in there, which means that you get to spend time with those people who are doing exciting research and who are also teaching you, and you'll be passing them in the hallways every day. So let's head inside. So this is the entrance to the main part where the first year classes take place. Let's head in. So this is the Tapas Area. So we don't actually serve any Spanish food here, unfortunately. Tapas stands for the Area for Physics and Astronomy Study. So this space is always available to students who are studying physics or astronomy. So you can get together with your classmates, work together on assignments, brainstorm ideas, lots of whiteboards to put your ideas up and try them out. So this Tapas area is actually surrounded by all the first year teaching spaces. So here at Monash, we've redesigned the learning in first year. Instead of having students go into a lecture theatre and learn about physics, we get them into some rooms where they can actually do some physics and figure out some of the principles themselves. So we'll head in. So this is one of the first year PACE studios where the classes take place. So when you're in this room, you do a mixture of activities. So part of the time you might be doing an experiment. You can see some experiments set up here. All the equipment is in the room ready to grab. You might be trying to figure out a physics principle from that experiment. You might be discussing with other people in your table how it works. You might be doing some problem solving, simulations. So we often have laptops on these tables as well, graphing the data as you go, having some content delivery. You can see we've got screens all around the room so that you can do interactive polls. You can put your results up to show the rest of the group. So it's really a very dynamic environment compared to the lecture theatre, much more interactive. And there's a lot of research, not just feedback from students, but peer-reviewed research that says this kind of learning environment gives much better outcomes in terms of your learning, as well as your experience of university. So really making sure that what you're getting is way, way beyond anything that you could get online. So you can see we've got some of the open day experiments set up here. So there's a whole lot of videos you can see at the Open Day platform, which will try some of these out. So you can see the details then. We've got gravity-defying wheel. We've got the levitating superconductor over here that Augustine will teach you about. We've got the gravity well just here. We've also got the impulse and momentum lab here and the jumping rings over here. There's also a nice fun one here with spinning stools, which is very fun if you get to come in and do it in person. And so Marcus will show you how these ones work with Amanda. So definitely check out those videos online. And one more over here we've got is the magnets falling through tubes. So I'd also recommend you check that one out. Okay, so that's these rooms here, and we're going to head to the next venue. Okay, so up here in this second, third year precinct, we actually start off with a lounge, which is sitting between the second and third year labs. So this is especially for physics and astronomy students who can come here to spend time socially, to work on assignments together, to learn from each other, and make sure that you get a really nice university experience beyond what you could get online. So making friendships and building connections with the other students as well. So lots of nice spaces here. And now we're going to head into the third year labs where you would be doing experiments. So here in the third year lab, there's a whole lot of really specialist experiments. So students can choose the topic that's most of interest to them and do the labs that are focused on that topic. We've got ones that you can come in here to play with equipment in person, and we've also got ones that you can do remotely. So this one here, the beta ray spectrometer, you can actually control it from home. So you can be sitting on your couch, driving the motors, watching with the camera, and get the whole experiment done there. So with this equipment, if you watch another video on the website for Open Day, you can actually find a lot more information about some of these specific labs with the head of department, Michael Morgan. I'm just going to give you a quick look through today here. So some of the other equipment you can see here, we can look at doing the Mossbauer effect right here, which is actually running, collecting data for a student who's at home. There's some equipment looking at antimatter down here. So this is the positron emission tomography experiment here, which is of course the basis for PET imaging. We've also got some nice big magnets over this side here, so measuring nuclear magnetic resonance, the basis of magnetic resonance imaging, or MRI, which you would see there. We've got some other huge magnets here for the magnetic susceptibility prac. And one of the setups that I think is really unique and quite fun to use is this scanning electron microscope. So instead of using visible light to take images, this one uses electrons, which means you get really high resolution. And the ability to just play around on one of these is pretty cool in a third year lab. And if you want the really kind of up-to-date modern one, you just head down to the research centre for electron microscopy down there. So we'll head out. So just the other side of the lounge that we were looking at there, we have the second year lab. So we're just going to look through here quickly. These ones change every semester with different experiments. So there's a few set up here in electromagnetism. We've got Fourier synthesis of musical instruments, so actually recording sounds from different instruments and then breaking up that sound signal into the different frequencies that make up that particular type of wave. And that Fourier decomposition is used in a whole lot of areas. So even in the medical imaging work I do, we use the Fourier transform to go from projections to CT images to try and analyse what information we have in there quantitatively. So some of these things that you might not necessarily see linking often do. We've got some spectroscopy here, so looking at the different energies of radiation that we get out of gamma sources and also X-ray sources here as well.
Hello, I'm Associate Professor Michael Brown from the School of Physics and Astronomy, and I would like to introduce you to our observatory, which we use for third year honours and master's astronomy units. The observatory consists of an 11-inch telescope and a 14-inch telescope, both of which are computer controlled and equipped with CCD cameras and tip-tilt adaptive optics. Monash students sit in the observatory domes controlling the telescopes themselves to obtain images of galaxies, clusters of stars, and stars with known exoplanets. The students also process the images themselves using the same methods as professional astronomers, and then they analyse their observations. Using their images, Monash students have determined the sizes, distances, masses, and ages of celestial objects. We have also used these telescopes to obtain spectroscopy of celestial objects, and students have measured quasars billions of light years from Earth and measured them moving away from us at tens of thousands of kilometres every second. Observations from this observatory can indeed measure the very expansion of our universe.
So this is the New Horizons Research Centre, so a huge building, many research labs with people from Monash Physics, from Monash Engineering, from the CSIRO, and there's all kinds of interesting things in here. We've got the coldest matter in the world, the boson condensates, in the physics labs, which is kind of behind this big bunker part here, so they don't have any windows because they need a really, really stable environment there in terms of temperature and space. We've also got people working on next generation materials as part of the fleet research collaboration. We've got some X-ray imaging happening right behind this wall here. So let's head in and have a look. So we've got a whole lot of research offices here on the first floor for physics. So if you do honours, you actually will have an office based in here. And then we have the research labs on this side here. So the labs that are down this end of the building are mainly part of FLEET, which is the Australian Research Council Centre of Excellence, so across multiple universities, a centre that's looking at future low energy electronics technology. So there's a number of research labs that they work in here, which we can explore.
Hi, my name is Jack Hellerstedt. I'm a postdoc in Augustin Schifrin's group in the School of Physics and Astronomy, doing research adjacent and themed to the FLEET Center of Excellence. I use scanning probe microscopy to take pictures of molecules. I'm interested in using molecular self-assembly to create structures predicted to host exotic physics.
So here in this laboratory, we have a special capability with this microscope. It's called non-contact atomic force microscopy. So with these microscopes, they're famous for taking pictures of single atoms, but we can also achieve sub-molecular resolution, which in layman's terms is taking a picture of a single molecule. So that's what you see on the monitor here. Here is a single molecule where we're resolving the chemical bonds. So you see, here's these two molecules, and an active scientific question that we're trying to answer is what's happening between them. We're specifically trying to determine if there is a metal atom between those two molecules. So in the larger context, we have extraordinary control at the single molecule and single atomic level, and we can also measure the electronic properties. So we can move these things around, we can change the physical structure, and then we can see what the result is on the resulting electronic properties.
What we do in these labs is growing two-dimensional materials one single layer of atoms at a time. We have microscopes that actually reach atomic resolution, and we can also study their electronic properties. I'm Yolanda, and I'm a postdoctoral researcher at FLEET, the Center of Excellence, and I work at Monash University.
Hi, my name is Chris Halmerson. I'm a chief investigator in FLEET, and I'm also a professor in the School of Physics and Astronomy at Monash University. So my field of research is basically atomic physics, but I also do some work in biophysics. And basically, most of my research involves applications of lasers. I use lasers to cool atoms to very, very low temperatures, just a few billionths of a degree above absolute zero. And I also use lasers to investigate properties of biomolecules and biomembranes. So in this lab, the research involves cooling gases to very, very low temperatures. So cooling gases to about a few billionths of a degree above absolute zero. And this is a typical apparatus used to do such work, which is called ultra-low temperature physics. We have a source of atoms down here, and this particular apparatus uses rubidium atoms. We shine lasers in through the windows, and this allows us to basically remove the energy of the atoms, which may sound a little counterintuitive because you usually think of lasers as heating or burning things. But there is a way to actually use lasers to cool atoms down. And then down in this part of the chamber, we actually have a collection of atoms that are at very, very low temperatures. When you get to these low temperatures, it behaves like a superfluid gas, and we study their properties down there. And this is the basis of superconductivity, where you can have electrical currents flowing without resistance. So the hope is by working with such systems, we might better understand dissipationless or low dissipation materials.
Hi, I'm Gary. This is our ultra-fast laboratory. Here we look at topological materials, so we're trying to use ultra-fast laser pulses to induce topological changes in various materials. At present, we've got a number of projects going. We're trying to induce topological changes in graphene's band structure using circularly polarized light and investigating those materials with terahertz pulses. I am particularly interested in the potential use of topological materials in next-generation low-energy electronics.
Hi, I am Shemunti. I'm a research postdoc in the School of Physics and Astronomy. I work in a group of materials called 2D materials, which are only one or few atoms thin. They offer extraordinary properties such as high conductivity, mechanical strength, extremely good optoelectronic properties. I stack these materials like atomically thin Legos to create new hybrid materials and experimentally study their electronic properties.